Welcome back. In lecture 10, we are now going to look at another approximation for the exchange correlation potential. And so far, we have done the LDA, local density approximation, and we are going to move now to a more popular exchange correlation approximation, which is the general gradient approximation. Just as a reminder, this is the equation that we came up with within the cone-charm description, where the energy functional, which we know exists according to Hornberg-Kohn theorems, we express this functional as a piece that can be computed from independent electrons. So that would be the kinetic energy and the Hartree. And then everything we don't know, everything we swept under the rug as part of this exchange correlation energy that's shown in red. The idea here is that at least we have the biggest chunk of the kinetic energy that's taken care of, and all the rest, all the correlation and quantum mechanical effect really are part of the exchange correlation. So in general, we can write this exchange correlation functional for the energy using this equation here. And so many people have been working on this over the years, and in particular, the group of Purdue who came up with this image there um, show in this image that you can actually calculate different types of approximations, starting from the local density approximation and the Hartree world really below that we introduced in the first few lectures of this series. And the first rung of that Jacob's ladder for exchange correlation functionals was the local density approximation. Now, during this screencast, we are going to climb one rung. We are going to go to the generalized gradient approximation. But let me give you maybe already an overview of what the different rungs are about. So the first rung is the fully local exchange correlation energy. We've spent quite a bit of time on this in the past lecture. The second rung is the one we are going to investigate in the screencast, is the semi-local general gradient approximation. And as you can tell from the function there, the new ingredient that we are putting into the equation is the gradient of the density. So we basically take into account the variation of the density, not just the value of the density at the point. We will spend a little bit of time also on the next rung, which would be rung like meta GGA. The meta GGA, as you can see, the additional ingredient, the last part of between the parentheses, is actually related to the kinetic energy of the calculated in the with the cone-charm orbitals. So this is still semi-local, but it provides more information by computing this kinetic energy. We'll spend a little bit of time on that in a future screencast. And then the rung 4, which is not the final one, but it's because there are more rungs until we obtain the full accuracy. But the rung 4, there are hyper GGA and hybrid GGA, for example. We'll spend a little bit of time on the hybrid GGA. This is pretty much the functional of choice that's used now, certainly in quantum chemistry, but not just. And we'll discuss that later. So when we will build these exchange correlation functionals, people historically have been looking at a number of properties that you want. So you know it's going to be approximated, but you want to have some features. We don't want to have an empirical derivation because we know the quantum mechanical concept, and then we want to do this non-empirical derivation. That means not using experimental data. That's not exactly fully true, as we actually going to see for GGA in some instances, but we really want to use the fundamental concept of quantum mechanics. We want this exchange correlation to be universal. And I'd like to insist on this again. Many people are using force field or semi-empirical tight binding, for example, which is uh, uh, really model Hamiltonians. But in those cases, usually, I mean, pretty much always, the parameters that enter, for example, in a force field are really specific for a class of system, or in fact, specific classes of system. So you need to use different parameters each time. For in the exchange correlation functionals, yeah, I like to insist on this. When we say LDA, we use LDA for everything. It can be atoms, can be different type of solid, could be metals, covalent, ionic. We really use always the same functional. I mean, the same given functional, and we do not fudge with the numbers depending on on the particular material we look at. So that's what we call bi-universal. That's one of the big strengths, of course, of LDA, because I mean, not LDA, of DFT in general, because, well, once you are an expert in DFT, you can really apply it to many different systems. We would like it to be simple, simply because if we add too many terms, we start to lose a little bit the sight on the physics and on the fundamental principles. So if we can do something simple, we can actually understand not only the applicability, but also the shortcomings and the failures. And of course, we want to have enough accuracy. Otherwise, it remains academic and not very useful. Just the good news about this is that the exchange correlation functional that we use nowadays are really accurate and not for academic purposes. So let me remind you a little bit of about LDA. In LDA, this plot I showed you a number of times before. On the left-hand side, we have the density, and the idea is that the exchange correlation energy is calculated just by the value of the density at a given point. So those two purple points on the left, which have exactly the same density but clearly correspond to different behavior of the density of the density, they actually correspond to the same energy, so that they would contribute the same way to the exchange correlation energy. So clearly, we showed that the LDA is actually fairly successful thanks to cancellation of errors, but that's clearly kind of a shortcoming, right? So that's what we do in LDA. Now, just remind you the equation that we've seen a couple of slides ago. The difference between exchange correlation in LD and exchange correlation in GGA is the introduction of the gradient of the density. In this version here, I actually wrote the density. I separated the density up and down to remind you that we can always do DFT with the spin up and spin down density of electrons and in general. So sometime you are going to, instead of LDA, you will see LSD, which is the spin densities. It's the same idea. These are just a different name. So you could think that very often in physics, what we do, we use Taylor series, right? And so we could consider that we start with LDA as being the first order approximation, and then we add um, correction like the first derivative, second derivative, and so on and so forth. So that would be an idea, and that would give the idea of a gradient expansion. But before I move on, know that this is not the right approach. If you actually do this and you add term one by one as a kind of a Taylor series type of approach, it is not actually working. This is actually not what is done. Um, it's even shown that if you do it this way, you barely improve over LDA. So maybe even sometimes even get it worse. But it turns out that what people realize is that you need to come up with functions that are a little bit more complicated of the gradient, higher power of the gradient, and that kind of things. So that's what was realized. Now, in the 80s, in the early 80s, and this is really when DFT took off, it's thanks to this development of GGA. It's particularly for chemists who were not satisfied with LDA at all. But GGA is changing the game a little bit, certainly historically, but also, I mean, reality is still today, even though, as I will show, we actually use what is called a hybrid GGA, but that's going to be for the next lecture. So people came up with sort of functions and not arbitrary functions, as I'm going to show you in a minute, that are based in general, involving the gradient. That's why we call it general gradient approximation. Not to confuse with the expansion, which would be a Taylor series type of approach, which actually doesn't work. So just to give you a visual explanation for this, if we go back to this plot, instead of just using the values at the values of the density at the purple point, we also take into account the gradient at those points, and this is actually going to make a big difference in the accuracy and quality of the functional. So one thing that you have to also realize is that there are different types of GGAs. I mean, there are so many possibility of coming up with functions with still a very high level of arbitrariness that there are many different types of GGAs. They're actually not just random, really. Again, I'm going to show you why they're not random, but there are different type of GGA. So if you write a paper and you say I'm using GGA, that's not enough. You have to say which actually GGA you are doing, as opposed to LDA, where LDA there's just one LDA. Okay. Just a quick remark is that sometimes there are different parameterization of LDA. This is really the same LDA. This is how you parameterize the quantum Monte Carlo result for the correlation for the correlation of an uniform electron gas, but this is really the same result. It's just a different parameterization of the function that represent those data. So that's LDA, there is one, GGA, there are many. That's basically what you have to say. So we obtain different type of GGA. And now there is a little bit of a difference between the approach that chemists would use and solid-state physicists. Chemists like to use those functions and develop very, very smart functions. And the parameters that they show in the functions actually obtained by fitting with a large set of selected molecules. But this is a very large set. And GGA is so well parameterized that it has the accuracy of the structures that were used for training. In fact, we could say that it's some sort of a machine learning, a regression type of things, if you want, before its time. But of course, before its time, this regression has existed well before machine learning or AI became uh, all the big hype that we know now. On the other side, solid-state physicists and physicists in general, they emphasize, instead of using sets of selected molecule to train, they emphasize exact constraint rooted in quantum mechanics. Um, Both types of GGAs in general, they yield a very similar result. Maybe there is a little bit more emphasis on the chemist GGA, on the bond length and that kind of things. But they yield very similar result. So many GGA have been developed over the years. For example, two well-known ones are PBE, which were P, B, and E stand for Purdue, Burke, and Erzenhoff. And these PBE is essentially pretty much the most used GGA functional in material science and solid-state physics. Chemists use BLIP, which is actually a mixture of the exchange functional from Becky along with the correlation functional of Li, Yang, and Parr. And again, the name BLIP is the first initial of the four authors. Just a little point. In fact, chemists do not use BLIP as much. They actually now use B3LIP, which is actually a hybrid functional. Again, we'll discuss that. I don't want to show that I have any any preference for different type of GGAs. There are many more GGAs than those two I'm just mentioning, but this is a good starting point. Some of them actually there are improvement even on PBE. There are revised version of PBE, for example. This is always interesting if it's something that's nice to do when you start with DFT to test a few of them and on a set of systems and see the difference that you get. There is a very broad literature about this topic, and I invite you to look at that. So there is no such thing as a GGA, different types of GGA. I'm just giving a list here that's far from exhaustive, but just to give you an idea, there was the Purdue one, for example, PW86, with different properties. There were Becky Purdue in the late 80s also, as well. LIP that I already discussed to you about that focus on the correlation. PW91 is also a popular GGA that was developed. that's purely ab initio in the sense that it doesn't use training set. I mentioned to you PBE, which is developed in '96 and is one of the most used GGA functional in physics, solid state physics in general. That was, as I said, revised to make it to make PBE also better for certain type of applications. So that's the possibilities are infinite. So as I mentioned to you, going back to those two famous functional like GGA functionals, BLIP is based on some very empirical parameters. It's basically a function that's well established, and the parameters of that function are obtained from training sets, if you will. PBE instead, they like to keep it first principle. It is used. It doesn't use any training set, but it uses a number of constraints that we actually have seen. Some of them we have seen before. I'm going to show you some of the constraints in the next slide briefly. But even with the constraint, there are still some arbitrariness in the parameters that you use in even in PBE. So the key constraint that I can mention to you, some of them we've discussed in terms of issues that we had with LDA. First of all, it works on the asymptotic behavior, especially when there is low energy density. If you remember, we have a system that should behave as 1 over r, the potential instead of exponential. So this is one of the things that's important. Another one we discussed a lot, we spent a lot on is the sum rules, which is the integration of the exchange correlation whole that integrates to -1. This is a constraint that it's imposed in PBE. We have also the constraint of GGA working also for slowly varying electron density. So that's an important thing. We also so again we want the different scaling laws that we discussed before briefly. This is also a constraint that's obeyed by GGA. GGA actually we know LDA is exact for uniform electron gas. Well, GGA, one of the constraints is GGA also at the limit of uniform electron gas will recover the same result. And also some work on the self-interaction errors that still, it's been plaguing this approach of DFT that we discussed so far. But GGA still has self-interaction errors, but there is some focus on reducing the self-interaction errors. And there are other energy boundaries from the exchange correlation energy that can be calculated from the fundamentals of quantum mechanics. So these are just a few constraints that are obeyed. And people who basically devote their entire career in developing functionals, they use those constraints and other constraints that are all fundamental constraints based on the physics, based on quantum mechanics. One of the constraints, if you remember, that we discussed at the last lecture when I discussed about the problem with band gap in DFT, the fact that the derivative of the exchange correlation with respect to the number of electrons in the system, which is, if you remember, there was a derivative discontinuity around the integer point. This one is not obeyed by GGA either as LDA. So as you would expect, the issue with the band gap in GGA is going to be just as bad as it is in LDA, and we are going to see that actually in a minute. So GGA has improved things significantly, and let's talk about the success and failures. GGA is pretty good with the chemical bonds. So at least the covalent, ionic, and metallic. Not van der Waals, as a future point is going to show. So GGA is an improvement over LDA. Again, can also account for the increased popularity of DFT in the early 90s, and that actually still survives today. The band gap are still underestimated for the reason I just gave you. It doesn't this discontinuity in the exchange correlation potential with respect to the number of electrons is still not there. So same issues. The band gap in GGA, the band gap in LDA are equally wrong, about 50%. And one thing that's important is that van der Waals, which is a non-local effect, is not present in semi-local or local approximation, well, like GGA and LDA respectively. So this is not there. And I'm going to show you even an example showing you that GGA is actually worse than LDA. Now, how could that be worse since LDA does not represent van der Waals? Well, LDA does not represent van der Waals well at all, but because of a constellation of errors, the numerical result you get are actually close to a situation where you would have good van der Waals. Okay, I discussed that already before. I'm going to show you an example of that also in a few minutes. But GGA now does not have the same constellation of errors for van der Waals. I'll put that between quotes because really there is no van der Waals in either. And so GGA would not even predict usually the appropriate interlayer distance, for example, in a 2D stack. The good news, and that's going to be the topic of a future screencast, is that many van der Waals correction to GGA has been introduced. I mean, like it's been a very hot topic, especially in the past 10 years or so. And now we have really the good corrections to GGA, so that GGA plus those corrections is doing pretty good with van der Waals, actually. But not GGA, plain vanilla GGA, if you will, does not do very well with the van der Waals. We are still far from chemical accuracy, but we are getting there. I mean, getting there closer. So one thing that's useful is to maybe compare GGA and LDA, and this table does that. Let's look at the bond length now. You remember LDA was overbinding. I mean, there was just too short bond lengths. GGA is not a huge improvement because now it's still about 1% wrong, which is not bad actually, but it's now usually overbinding. GGA typically overbind. GGA is pretty good with structures, so with like like unit cell size, mechanical properties, and that kind of thing. And most importantly, the energy barrier for chemical reaction or absorption, and that kind of things. Now GGA is still low, but it's semi-quantitative now, so that's nice. And you can see that improvement in GGA by looking at atoms. If you look at some benchmarkings on some of those light atoms there that we have in this table, you can see directly that the total energy, which is of course the expectation value of the energy, right? Which is of course a key quantity in DFT. LDA doesn't do too bad. Right here, it's written LSD, as I mentioned before. It's LDA, but with spin polarized, so the spin is included there. It's another way to call LDA for spin. The energy for LSD or LDA, it's actually not bad at all compared to the exact one. I mean, it's not terrible at all, you can see. But GGA is a significant improvement. Now, GGA provides at least 2 digits of accuracy compared to exact, which is tremendous, really tremendous. So I mentioned to you that GGA is an improvement for lattice constant and cohesive energies, for example. And you can see here example of comparing experiment. So let's focus on the left-hand side on the lattice constant here. The experiment is shown in a straight line. As we expect, LDA doesn't do a bad job at all in the orange dots, but always overbinding, so it's always smaller than it should be. GGA is typically higher, typically overbinding, but not as bad. So this is for the lattice constant. The bond length is about also 1%. It's still in the same ballpark of errors, but it's reduced, right? It's still the same kind of behavior, but it's significantly reduced. And then the same thing for cohesive energy, which are related, of course, to total energy. We just showed on the previous slide that GGA does better, and indeed, it does significantly better. Now, related to the hole, to the exchange correlation hole, we know that both LDA and GGA have the right integration of exchange correlation hole density to -1. But the asymptotic behavior of GGA compared to exact for both the exchange compared to Hartree-Fock, which is exact exchange, or the exact result for the correlation hole, GGA does better asymptotically. So which is, of course, a very good behavior. So that's nice. So GGA does very well for the core electrons where they have a higher density. So that's good. GGA treats the difference between the core and the valence electrons well. The energy barriers are much improved with GGA, so that's nice. So as I already mentioned, GGA lengthens the bond a little, but very accurate. And GGA favors inhomogeneity. So that's why it improves a little bit um, what we see, for example, in atoms and molecules, and again, why it has been more adopted by chemists compared to LDA, for example. Now, if we look at band gap, just to confirm what I told you, that the band gap of GGA is still uh, significantly underestimated, up to 50%. We see this in this plot. So we usually plot, this is the typical plot I've shown you before, where we compare the experimental band gap with the calculated band gap. And if we had 100% accuracy, all the data points will be on the bisector, so the dashed line. So let's not look at the green dots just yet. Let's look at GGA. So you can see that for those, here I picked an example of binary compound from this paper in 2019. And all the band gap, they follow the trend of the experiment. They are not bad. They are semi-quantitative, but they are typically underestimated. So in a future lecture, we'll talk about HSE. HSE is actually hybrid functional. And it's still not perfect, but it's a significant improvement compared to GGA. And now we can talk about beyond qualitative, it's pretty much quantitative result. Now, a failure that I want to discuss as well, I already mentioned van der Waals, but now I would like to illustrate this. So this is an example from this 2010 paper where people were studying the graphene adsorption on a iridium 111 surface. And I want you to focus a little bit for a second on the blue curve, which is LDA. Both LDA and PBE are not very good with van der Waals. I mean, they're not good at all. In fact, there's no van der Waals. But if you look at LDA, there's a shallow minimum, which is around 3.4 angstrom. You can see it's a minimum because it goes down and then it goes back up to the dotted line. So it actually predicts the right length again for cancellation of errors. PBE, it's obvious that PBE is not good with van der Waals, but in this case, it's obvious too because there's no minimum. Actually, it keeps going down. So in other words, in PBE, a piece of graphene and iridium would be happy to be at infinity, at infinitely away from iridium. And I mentioned to you corrections to the van der Waals, to the PBE using van der Waals correction. It's the red curve is an example of that. The red curve is basically PBE plus a type of approximation to van der Waals. We will discuss much more the van der Waals correction in a future screencast. But the idea here is that it's possible to improve upon that significant failure of PBE. So I hope this screencast was useful to you to introduce you to GGA. So just to summarize, we have strength of GGA, improvement compared to LDA, certainly less overbinding, better energy barriers, pretty good for molecules actually, but still very good for solids. So that's really the best of both worlds. We still have the shortcomings. Sometimes we have underestimation of the binding, underestimation of the band gap, just like LDA, no van der Waals. The other box there about more computationally demanding, that was more acute problem before computers were capable of handling this. Frankly, now you do not see a significant time difference when you do a calculation in LDA and GGA. This is not very significant, the difference in time. So that concludes this screencast about GGA. In the future screencast, we will look at at other functionals. We spend one screencast on other functionals, and then we will look at van der Waals corrections to GGA in another screencast. I thank you very much for your attention.